In previous chapters, we classified ionic compounds as either soluble or insoluble in water. Like many other subjects, the distinction isn't so black and white. In this chapter, we will study the implications of slightly soluble compounds. For example, let's consider calcium fluoride. As a convention, we always write the solubility equilibria, or the reaction for this process, with the solid as a reactant and the aqueous ions as the products. The equilibrium expression for this dissolution would be labeled as K equals calcium 2 plus ion times the fluoride ion squared for that 2 in the balanced chemical equation. Since the solids are never written in equilibrium expressions because they don't affect the position of equilibrium, we refer to the constant as the solubility product constant, and we'll put a little SP at the bottom of the equilibrium constant to designate that. Again, that's the solubility product. Please also notice the math term product. This means we don't ever have anything dividing. One of the most common questions that we'll encounter for solubility equilibria is whether or not a precipitate will form. Just like reaction quotient problems in our previous chapters, we're going to need to compare the Q versus K. In this scenario, the Q would also be equal to the calcium concentration times the fluoride concentration squared, except that these concentrations are at initial conditions, or in the I part of a rice table. In general, if the Q is less than the KSP value, this is considered an unsaturated solution, where more of that compound can dissolve. You can think of it as an equilibrium shifting to the right. If the Q is equal to the KSP, that means you're just perfectly saturated, or no more can dissolve. You can think of that moment where Q equals KSP as a tipping point, where if you had any more solid inside of your solution, you would actually have little precipitates at the bottom, and if you had any less, you would be unsaturated and you could fit some more ions inside of your solution. If your Q is greater than the KSP value, you have a supersaturated solution, or way over the max. In this case, your equilibrium will naturally shift left to compensate for being supersaturated. If you have a supersaturated solution, you're going to create a precipitate, or a solid at the bottom of your container. Often, when I'm writing precipitate, I'm going to abbreviate with a PPT. This is common notation. Feel free to use it. Okay, let's try an example. Let's say the question is asking us if a precipitate will form if you mix 10 milliliters of 0.010 molarity calcium nitrate and 10 milliliters of 0.0010 molarity sodium fluoride. Okay, My first thoughts to tackle this question are which ions are actually going to be precipitating or possibly precipitating. So I'm going to write down everything that I have in my beaker. I know from previous chapters that certain ions, like nitrate and sodium, are always soluble, so they're not going to participate in precipitating. This means that my molarities, as long as they're 1-to-1, are actually of my calcium 2+ ion and my fluoride ion. Okay, now that I've thought about that, I need to think about the fact that I'm mixing two different solutions. Each of my samples is going from being 10 milliliters to having a volume of 20 milliliters. So what I'm going to do is calculate the moles for each of my particular species by multiplying the volume times the molarity to get 0.00010 moles of calcium and 0.00010 moles of fluoride. And I'm going to divide both of them by my new volume of 0.02 liters. This gives me a starting concentration for calcium, that is 0.005 molarity, and for fluoride, 0.00050 molarity. Okay, now to see whether a precipitate will form, I need to calculate the reaction quotient. I'll use the expression that we used earlier. Calcium times fluoride, and then remembering to square because there's a 2 in front of fluoride in the balanced chemical equation. Okay, so when I enter my numbers, 0.005, 0.0005 squared, punch that into a calculator, and we end up with a value of 1.25 times 10 to the negative 9. Now, to figure out if this is going to work, I need to compare this value with a known K value. So I crack open a textbook, look up all the KSP values, find calcium fluoride, and write down that value is 4.0 times 10 to the negative 11. Okay, so when we're looking at these two numbers, we need to figure out which one is bigger. 10 to the negative 9 is a bigger number than 10 to the negative 11. So right now, my Q is greater than my K value. This indicates that I actually have too many things on the product side of my equilibria, so my reaction will shift to the left to relieve this stress to get towards our equilibrium constant. In this case, that means we're going from only aqueous species existing to creating a solid, which means a precipitate will form. So Q is greater than K, so the reaction produces a precipitate. Whenever you need to prove if a precipitate is formed, you need to perform a calculation of the reaction quotient so that you can compare it with the solubility product constant.